Yes, some software information comes in. That's a license agreement. So maybe I click. It didn't come before.
Click stop sharing first.
Huh? There's no sound these days. It should be. Can you hear me now? Oh, yeah, okay, thanks. Yep. Hi, Mark. You have joined, I noticed. Hi, everyone. We shall start 5 past hour, right? Okay. Hi, everyone. Can we start now? Today, I'm going to go through chapter 2B. And today and also Friday as well, we'll cover the material on chapter 2B on integration of rational function and partial fraction technique. Okay. Now, first definition. Now, a rational function has the form px over qx, where P is a polynomial function and Q is a polynomial function. So it's a fraction of the form Px over Qx. P and Q are polynomials. So let me remind you the definition of the polynomial function. I'm sure you would have seen in algebra as well. Now, so a polynomial function is a function of the form Px equals an x to the power n, an minus 1x to the n minus 1, and so on up to a1x plus a naught. A is real numbers, okay? And n is a non-negative integer. N is a non-negative integer. And for example, if an is non-zero, then the highest power is x to the power n, so that's an nth degree polynomial, okay? So you would have seen, so for example, Px equals 2x cubed minus x squared minus 4x plus 1 is a polynomial of degree 3. The highest power is 3 there, okay? So this is actually nth degree polynomial. And we say that a rational function is proper whenever the degree of the polynomial of the top, Px, is less than the degree of the polynomial of the bottom, Qx. Okay? The rational function is proper. The degree of the polynomial of the top, Px, is less than the degree of the polynomial of the denominator, Qx. Then we say the proper rational function. In fact, later on, we will be looking at method of partial fraction for proper rational function. So I want to give you some example first. So any rational function can be integrated by systematic reduction of partial fractions. So that's the technique we are going to go through today. Okay, here are some examples. Here, let's go through this example here. So written down 4 of them. Let's look at whether they are rational function or not. Rational function and proper rational functions. Let's look at the first one. So it's 2x plus 1 over 3x squared minus 4. So the degree of the polynomial at the top is 1. What was the constraint for B? So I'm going to look at here. First, identify the rational function, which ones are rational and which are proper, and so on, right? So the degree of the polynomial at the top is 1. Degree of the polynomial at the bottom is 2. Here. So this is a polynomial, that's a polynomial, therefore it's a rational function. That's correct. And is it a proper rational function? Yes, because the degree of the polynomial at the top is 1 and the bottom is 2. That's less than the degree of the polynomial at the bottom. So that's a proper rational function. This is not a rational function because cosine x is not a polynomial. So that's not a rational function and certainly not a proper rational function as well. Now what about this one here? C, x squared over x squared minus 1. So the numerator is a polynomial of degree 2. Denominator is also a polynomial of degree 1. Certainly it's a rational function. Is it proper? No. The degree of the polynomial at the top is higher than the degree of the polynomial at the bottom. Right? So it's not a proper rational function. What about this one, last one? E to the x over x plus 1. Is e to the x not a polynomial? What about the numerator have more than 1x? Yes, you can have that as well. We will look at more examples like that later on. So here e to the x is not a polynomial, so that's not a rational function. That's not a rational function. Okay? So rational function means the highest power of the polynomial. Power of a polynomial, right? So here's a polynomial 3x squared minus 4. There's no x term here. What's the difference between proper rational and normal rational? That's the difference here. So this one is if you look at part C here, that's the rational function, but it's not a proper rational function because the degree of the polynomial there is higher than the degree of the polynomial at the bottom. Okay, we have the degree of the polynomial. Degree means the highest power of the x term there of the polynomial. Okay, so these are some examples just to figure out which ones are rational and proper rational function and so on. So first thing we need to do, the function, for example, this one part C is not a proper rational function. So we need to first convert that, rewrite this in terms of a proper rational function as well. Okay, let's look at an example to see how this can be done. Have a look at this function here. Integral of 2x cubed plus 7x squared plus 3 over 2x plus 3, right? Now, see the degree of the polynomial in the top there is 3. The bottom one is 1. What EX is not a, so a polynomial means you have a finite sum, right? A next to the n up to a1, a naught. So e to the power x is not a power of x. Okay? So this one is not a rational, proper rational function because the degree of the polynomial of the numerator is higher than the degree of the polynomial, the denominator. So what we need in this case is just to apply the polynomial division. We apply the long division polynomial to write the improper integral into sum of a polynomial plus a proper rational function. Okay, let's see how we can do this here. So this one is not a proper rational function, so I'm going to apply a long division. You know that long division over here, 2x cubed plus 7x squared plus 3. You divide by 2x plus 3. Okay, and that gives you x squared. So 2x cubed and plus 3x squared. You subtract that, so that's 4x squared plus 3. And another factor here, x squared plus we have 2x there, plus 4x squared plus 6x here. Okay, subtract that, you get minus 6x plus 3. Just to confirm, condition of being rational is that the top and the bottom. Sorry, let me look at the question. The top and the bottom are both polynomial. Condition of proper rational is that degree of the top. Yes, exactly, you're right. Okay, now minus 3. Minus 3, so minus 6x minus 9. So that gives you 12. Okay. Yes, so now we can write, which is the polynomial division, 2x cubed plus 7x squared plus 3 over 2x plus 3 equals, you have x squared plus 2x minus 3, and the remainder is 12, and 12 over 2x plus 3. Okay, so by long division, I have rewritten this as a sum of polynomial plus this one here, the second term, 12 over 2x plus 3. So degree of the polynomial here is denominator is 1. The top is just a constant. So that is a proper rational function. Then we can integrate that as well. We look at the integration in the next example. So now we look at how we can rewrite that as a non-proper rational function into a sum of a polynomial plus a proper rational function. Okay, so that's simply apply the long division. Now, what we're going to do, we're going to look at how we can write the proper rational function into a simple sum of simple functions. So that this is the basic idea of method of partial fraction. Okay, let's start with the building an intuition and how you can develop this scheme. Have a look at the simple example here. So an integral like 1 over x minus x times 1 minus x, if you look at that here, so it can be easily computed directly from the table of integrals, for example. Okay, this is 1 over x times 1 minus x. You cannot straight away write down the answer there using the table of integrals or something. So on the other hand, if you look at the simple fractions like 1 on x dx, we know what the integral is, and 1 over 1 minus x also we know what the integral is. We can use the table of integrals as well. So the question is, So if you can write this rational function 1 over x times 1 minus x in terms of simple fractions like 1 on x and 1 on 1 minus x, then we can easily integrate them, right? So can we do that? So this is the question. Can we write 1 over x times 1 minus x? That's a proper rational function, by the way. So the degree here, denominator is 2, on the top is just constant, and some linear combination of 1 on x and 1 on 1 and 1 over 1 minus x. Can we do that? What's the answer here? Can we? Yes, you're right, side. So you can write simply, for example, 1 over x times 1 minus x can be written as actually 1 on x plus 1 over 1 minus x. Right? You check that here, 1 minus x plus x, so it's 1 over 1 minus x. So we can write this rational function as a sum of simple proper rational function here. But these two terms can easily be integrated. So this is the idea. Okay. The question is whether we can do this for any proper rational function or not. Yes, answer is yes. And that's where the algebra plays a role. So there's a theorem in algebra which says that any proper rational function can be decomposed or expressed in terms of some simple fractions. So here's the slide here. That is, but you don't have to remember these. There's some. You will look at some examples later on. So we can show that every proper rational function can be written as a unique sum of functions of fractions of this type: a over x minus a to the power k. K can be a number, say 1, 2, 3, and so on. I mean, most of the examples we will be looking at k from 1, 2 up to 3. Okay, or in the form bx plus c over x squared plus bx plus c. Now, this one is it's called irreducible quadratic factor. That means it cannot be factorized any further. So that means the x squared plus bx plus c equals 0 has no real root. Or in other words, b squared minus 4c is less than 0. Okay, that is called the irreducible quadratic term here. So you can write a proper rational function in terms of fractions like this or fractions like this. Now, for example, if we look at x squared plus x plus 1 is a reducible quadratic function because you can factorize into linear factors, right? So b squared minus 4ac here, 1 squared minus 4 is less than 0. There's no real root for x squared plus x plus 1 equal to 0. Okay. Another example is x squared plus 4. That is also a reducible polynomial. These are examples of irreducible quadratic terms. Okay. Now I'm going to give you some example of how this the decomposition of the sum will look like. Okay. So this sum is called the partial fractions decomposition of a function f. So if you have a proper rational function, we can decompose into partial fractions of this type here. Okay. Now, then we can easily do the integration of these simple fractions. Let me give you a template of examples of decomposition, right? And then I will go through all the examples later on. Here are the template. Don't need to take it down. Have a look at this here. We'll go through. Before I put that the decomposition here, I'm going to tell you about this proper rational function here. Now you want to notice three things here before we go on to look at the decomposition. Now, first of all, you see each of these rational functions are proper rational functions. So here, the degree of the polynomial at the bottom is 2, so that's fine. The top is 1. Top is actually constant. If you look at this one, the degree of the polynomial at the top is 2, and the degree of the polynomial here is 3. Right? When you expand it, you got x cubed and so on. Right? So that is a proper rational function. And same as the third one as well. 3x plus 2, and that's degree 1 on the top. On the bottom, degree here 2 and 1, the degree 3. So that's fine. Degree is higher than the first one. Same as the last one here. The last one here, the top degree of the polynomial of the numerator at the top is 3. Here, x squared to the power 2, that's x 4. That's fine. So all these functions are proper rational functions. Now, the second thing you want to notice here, the denominator denominators here have been completely factorized. You cannot factorize anything further here. X minus 2 times x minus 3. Same as here, x minus 1 cube, right? So the denominator has been completely factorized here. This cannot be factorized anything further, right? X squared plus 2x plus 2, b squared minus 4c, 4 minus 8 minus 4 minus 4 times 2, 8 is 10, 0. There's no real root 4x squared plus 2x plus 2 equals 0, right? So you cannot be written in terms of as linear factors, okay? So therefore, same as here, x squared plus 1 is a reducible quadratic term here. So that means the denominator here has been completely factorized. That's the second thing you want to know. Third one, you see the type of the factors you have. Because we will see the partial fraction techniques relies on the factorization of the denominator and the type of factors you have. So that's important to understand that. So if you look at the first one here, you have a linear factor, x minus 2. Linear factor is a factor of the form, for example, ax plus b is a linear factor, or 2x plus 3, right? Or x minus 4, they are linear factors. So this is, x minus 2 is a linear factor, x minus 3 is a linear factor. They are distinct linear factors, right? They are not repeated, x minus 2 and x minus 3. Now, if you look at the second one here, it's a different type. It's a linear factor which is repeated 3 times. This is a repeated linear factor. So this one is a distinct, maybe I write it here, distinct linear factor, the first one. Here, the second one, x minus 1 cube, the repeated linear factor. This one is a repeated linear factor. Because x minus 1 is a linear vector, it's repeated 3 times. Now, if you look at the third one, you have a linear factor, you have the product of the linear factor and the reducible quadratic factor, this one, okay? And the last one, this is a repeated quadratic factor, a reducible quadratic factor. We will go into details later on. I will do each of these examples completely later on, today and Friday as well. So at the moment, so these are the 3 things you want to notice. Now, using the theorem we have seen, we can write, for example, the first one can be written as a sum of simple fractions like that. A of x minus 2, b of x minus 3, if you have distinct linear factors. We will go into details later on. There's a question about how to find this a and b. Yes, we will be looking at that. Next to linear, distinct linear factors. Distinct linear factors. Okay. And if you have a repeated linear factor, you have 3 terms here. Don't worry about this, the format here on the right hand side. I'm going to explain it when I do this example. So we have the factors like that. You have 3 terms, simple fractions. Now, if you have this product of linear factor and the reducible quadratic factor, we're going to have terms like that, a of x minus 1. When you have a reducible quadratic factor, we're going to have the remainder can be a degree 1 polynomial. So bx plus c of x plus 2x. Don't worry too much about this fraction. I'm going to go through it again when I look at this example. So the partial fraction techniques crucially depends on the factors in the denominator. Okay, so we will look at several cases of different types of factors you can come across in this method of partial fraction. All right, so start with the first example. So first one is a very simple case. The denominator qx has a simple single linear factor. So alpha is a constant. So alpha is a constant. Okay. So, and you have already unrepeated single linear factor x minus a. We have come across an example like that. If you look at the previous example, so this term here, the denominator 2x plus 3 is a single linear factor. You can actually, if you want, you can rewrite this 2 times x plus 3 and 2. Right? Which is 2x plus 3. So this is of the form like this. So this, which we can easily integrate that, right? So for example, let's do the integration now. And this is the proper rational function. So in this case, so let's look at this integral here, x squared. It's pretty simple integration, dx. Integrate term by term. 12 over 2x plus 3x. Okay? So that's a simple polynomial, x3 over 3, x squared here minus 3x. So this is 6 times log 2x plus 3, right? Plus c. Because when you differentiate denominator 2x, you get 2. So you can write 12 here, 2 times 6. So then you get 6 log 2x plus 3. So this one can easily be integrated. So first case is a very simple case, right? So this can be done in general. In the next slide, I give the general formula, but you don't need to worry about this general theory here. But we will look at these things in example. So if you have a single linear factor like that, so you are looking at the polynomial rational function, for example, Rx over Qx, right? So what should be the degree of R here? Because Qx has degree 1, right? If it is a proper rational function, what should be the degree of Rx? Rx should be 0, right? Because this is a proper rational function. You're correct. Good, Sean, you got it right. So therefore, Rx should be constant. So you can write this. Rx is simply you can write it R over Qx dx. So Qx has the form alpha times x minus n. It's a very simple integral. The alpha is a constant, R is a constant. So this one is R over alpha times 1 over x minus a dx. If you have multiple logarithmic expression in your answers, it will probably combine them into one. Not necessarily. You can leave it as it is, fine. If sometimes you have to put the limits on, then you can simplify them when you put the limits of integration. Definitely not. Okay, so that's a simple integral. R over alpha log x minus absolute value of x minus a. We assume x is not equal to a. We have done an example run. So that's a very simple case. Let's look at the interesting case. Next example. This is 1 over x minus 2, x minus 3. Let's see how we can do this. Now, first thing you want to check the degree of the polynomial at the top and the degree of the polynomial at the bottom. X minus 2 times x minus 3. So that's the proper rational function. That's fine because the denominator is degree 2 and the top is constant. So, and second thing you want to do is you want to check here whether the denominator has been completely factorized or not. Yes, it has been completely factorized. You cannot factorize anything further. All right. So if you have a distinct linear factors, you can write this as in terms of simple factors like 1 over x minus. So that's a over x minus 2. We don't know exactly what the constant is going to be. And b over x minus 3. We can write it in terms of simple fractions like that. Okay. So we need to find a and b, right? So what we want to do to find a and b, so we multiply each side by the denominator so that we can clear all the fractions. It's easier to work with polynomial. So multiplying each side by the denominator here, x minus 2 times x minus 3. Okay, so in this way, you get rid of all the fractions, right? So I get 1 equals a times x minus 3 plus b times x minus 2. Right? We have a polynomial. This is true for every x. This is true for every x. Okay, now the question is how do we find a and b, the constant here? So here's a simple one. We can easily find a and b. So how do you find a and b? To find a, you substitute, for example, this is true for all x. Yes, you're right. For all x. So substitute x equals 2, both are the equation, so that gives you 1 equals a times, and just give 2 minus 3, and this one is 0 when you substitute that. So that's going to give you a equals minus 1. I'm going to write purposely here, a equals 1 over 2 minus 3. In fact, that's minus 1. I'm doing this purpose, you will see in the next slide why I'm doing this here. Okay, that's minus 1. So now to find b, you substitute x equals 3, right? Okay, put x equals 3. Then you get, that is 0, plus b times 3 minus 2. So that's 1, so that's going to give you b equals 1. So I'm writing here b equals 1 over 3 minus 2, which is 1. Okay, so we got the decomposition now. So 1 over x minus 2 times x minus 3 can be written as A is minus 1 over x minus 2. B is 1 over x minus 3. Check that your calculations are right. Your minus x plus 3 plus x minus 2, so that's 1. That's 1. So that is correct. Now you can integrate it easily, term by term. 1 over x minus 2, x minus 3 dx equals minus 1 over x minus 2 dx plus 1 over x minus 3 dx. Simple integration. So that gives you minus ln absolute value of x minus 2 plus ln absolute value of x minus 3 plus c. Okay? Now, I'm going to redo this question again and see how we can easily get this constant. Okay? So that's fine. All right. So let's do this question again. And we'll come up with a simpler method to do this. Could you use simultaneous equation? Yes, we will have to use it later. We'll see. There are some examples we will have to solve simultaneous equation as well. Okay, so I'm going to consider again 1 over x minus 2, x minus 3. We want to write it sum of simple fraction x minus 2 plus b over x minus 3. Okay? Now notice here, x minus, the a corresponds to x minus 2, right? On the left-hand side, you cover x minus 2 and substitute x equals 2. So that gives you 1 over x equals 2 minus 3. So that's what exactly we have done before, which is actually 1 over minus 1. Okay? To find b, b corresponds to x minus 3. You cover x minus 3 here and substitute x equals 3. So 1 over 3 minus 2 over x minus 3, which is 1. That's what we got. So that gives you minus 1 over x minus 2 plus 1 over x minus 3. So that was the decomposition we have got when we calculated. Let me show you the previous calculation. See, a equals 1 over 2 minus 3, b equals 1 over 3 minus 2. So this is called the cover-up rule. This is known as the cover-up rule. So to find a corresponds to x minus 2, to find the constant a, on the left-hand side, you cover x minus 2, substitute x equals 2. So 1 over 2 minus 3. And same is here, x minus. B corresponds to x minus 3, cover x minus 3, and sub in x equals 3, 1 over 3 minus 2. All right, I'm going to do one more example to illustrate the cover-up rule. How could you get a and b for second method? You mean here? Yes, so this is the cover-up rule I'm going to for the second. Yes, okay. So now we want to find a. Let's say you don't know this, right? We need to find the constant a, right? So that a corresponds to x minus 2. Now look at the left-hand side here. On the left-hand side, you cover x minus 2 on the denominator and substitute x equals 2. When you substitute x equals 2, 1 over 2 minus 3. That's what we got. Okay? To find b, the b corresponds to x minus 3, you cover x minus 3 on the left-hand side and substitute x equals 3. 1 over 3 minus 2, which is 1. That's what we got here. This is called the cover-up rule. So I'm going to apply it again in another example. You'll see how that works. Okay? Have a look at the third example here. Yes. Have a look at this here. This example. We have 3 factors here. 2x squared plus 2x minus 6 over x minus 1, x plus 1, x minus 2. Okay? Now, the first step you want to do here is to check the degree of the polynomial on the top and the bottom. Degree of the polynomial on the top is 2. Degree of the polynomial on the bottom is 3. We have x cubed there, term there. So that means a proper rational function. So we are ready to apply method of partial fraction. The second thing you want to check, the denominator has been completely factorized or not. Yes, it has been completely factorized. You cannot factorize any further. So we are now ready to apply. So here it's a product of distinct linear factors. You see that they are not repeated. X minus 1, it's not repeated, x plus 1. They are distinct linear factors. If you have distinct linear factor, for each linear factor, they correspond to one simple fraction. Okay? If you have for x minus 1, unrepeated linear factor, there should be a fraction a over x minus 1. X plus 1 is a different linear factor, unrepeated, there should be a corresponding fraction b over x plus 1. Same as here for x minus c over x minus 2. Now the question is, how do we find a, b, and c easily? So I'm going to apply the cover-up rule. I mean, you can also eliminate the fractions and then substitute points and so on. But the cover-up rule is much more easier. You can do it very quickly. Here's the cover-up rule, how that works. So the cover-up rule to find a, for example, here, a corresponds to x minus 1. For a, you cover up x minus 1 and substitute x equals 1 to the left-hand side. Okay? So a equals, on the left-hand side, you cover x minus 1. Here I am covering my x minus 1 and substitute x equals 1. So 2 times 1 squared, that's 1. 2 times 1 minus 6. And here 1 plus 1 and 1 minus 2. So that will give you the answer here. That gives you 4, that's minus 2. And here 2 times minus 1. So that's minus 2, that is 1. So a equals 1. Okay? So let's, for b, for example, for b, you cover up x minus x plus 1. b corresponds to x plus 1. You cover up x plus 1 and substitute x equals, what's the substitution here? Yes, correct. X equals minus 1 to the left-hand side. Okay, so that gives you b. So that means, because I've shown you in the first example how the constants were calculated by clearing the fractions. That's how it will work exactly. Right? Okay, so b. So to find b, you cover x plus 1 here. You cover x plus 1, substitute x equals minus 1. So 2 times minus 1 squared and 2 times minus 1, minus 6 over, and minus 1 minus 1 minus minus 1, and minus 1 minus 2. So then you get here, what do we get here? 2 minus 6. That's here minus 2 times minus 3. So that's plus 6, minus 6, so that's minus 1. That b is minus 1. Now, for c, you cover up this is x minus 2, cover up x minus 2, and substitute x equals 2, right? Okay. So that c, you cover up here x minus 2 here on the left-hand side, on the term there, you can see, and substitute x equals 2, that is 2 times 2 squared plus 2 times 2 minus 6 on the denominator, it's 2 minus 1 and 2 plus 1. Okay, so that gives you 8 plus 4 minus 6 over 1 times 3, so that is a 2. So we got that. So this is just a fast way. You're right. So now we can do the integration pretty easily. So what we have done, we have found a, b, and c. So now I can write the given integral. Let's see, you can see it here. So integral of 2x squared plus 2x minus 6 over x minus 1, x plus 1, x minus 2 dx. Now integration a equals 1 over x minus 1 dx plus b equals minus 1 over x plus 1 and c equals 2 over x minus 2 dx. So that's a partial fraction, you integrate it. Now we can integrate term by term. That's pretty simple. 1 over x minus 1 dx, 1 over x plus 1 dx, and 1 over x minus 2 dx. So that is given from the table of integrals, log x minus 1 x minus 1 minus log x plus 1 plus 2 log x minus 2. It's a good question, Miguel. They could have taught in the high school as well. Okay. All right, so that's how we deal with the distinct, if you have a distinct linear factors in the denominator, that's how we deal with that. Okay, now, so this idea will work more generally as well. So you don't need to worry about this general theory here, but I'm just going to give you a more general situation as well. If the denominator has, x minus a1 up to x minus a n distinct linear factors, x n distinct linear factors, you are going to have n simple fractions, right? We have n distinct linear fraction, linear factors, you are going to have n. So for this one, you get one fraction x minus a1. For x minus a2, you have another fraction, and so on up to n simple fractions. Okay? Then you can easily integrate that. So the question is how to find a and b. The answer here I'm going to use cover-up rule. Just to use cover-up rule, pretty easy to do. It doesn't matter how many terms you have. The cover-up rule will work. Okay? So let's find the first case. Now the second one I'm going to look at is the repeated linear factors. Have a look at this here. The second example here, 3x squared minus 3x plus 1 over x minus 1 cubed. Now, the first thing we need to do, as we did before, degree of the polynomial at the top and bottom. The top is degree 2, bottom is degree 3, so that's fine. Degree of the polynomial bottom is higher than the degree of the polynomial at the top, so that's the proper rational function. The second thing you want to check is that the denominator is completely factorized or not. Yes, it is completely factorized. So now the question is, how do you write this as a sum of simple fractions? Okay, let's look at that. 3x squared minus 3x plus 1 over x minus 1 cubed. Okay, so this is the denominator here is repeated 3 times. So you can think of this. So you have x minus 1 is a factor, x minus 1 squared is a factor, x minus 1 cubed is a factor. So then the corresponding fraction is going to be a over x minus 1, b over x minus 1 squared, plus c over x minus 1 cubed. So that's the partial fraction decomposition when you have a repeated linear factor. Okay? Yeah, repeated linear factor, you have, it's repeated 3 times, you're going to have 3 terms. A over x minus 1, b over x minus 2, 1 squared, c over x minus 1 cubed. So you can think of this as x minus 1, so vector x minus 1 squared, the vector x minus 1 cubed, so like that. Another reason for this decomposition is, you know that you remember the decimal expansion of the rational numbers? For example, look at this in the bottom of the screen here. We have the decimal expansion of the rational numbers. We have 267 over 10 cubed, right? How do you write that? 2 over 10, 6 over 10 squared, 6 squared, 6 over 10 squared, 7 over 10 cubed, right? So it's like that. So this is similar to this idea. Decimal expansion of the rational numbers to this. Okay, so we got that decomposition here. The next question is, how do you find A, B, and C? Okay, the first thing is to just multiply by the denominator so that we get a polynomial, right? Which one? Yes, they are there in the notes. Yes, multiplying each side by x minus 1 cubed. So in this way, you clear all the fraction. Yes, that's right. It's true. X minus 1 cubed. So then we get 3x squared minus 3x plus 1 equals, when you multiply by x minus 1 cubed, you have a over x minus 1 squared, b times x minus 1 plus c. Okay. Next to x, x minus 1 cubed. Yes. Okay. So you have, now this is true for all x, right? You have a polynomial equations here. There are several ways you can find the function A and B. You can compare like powers both sides, or actually there's you can substitute some values, some nice numbers. It will simplify. So it depends on which one you prefer. Actually, in this case, there's a simple method to find A, B, and C. So I'll show you how that's done. So first thing here, we can easily find C, right? So how do you find C? You substitute x equals 1, right? Yeah. Substitute x equals 1, both sides. Substitute x equals 1, 3 times 1 squared minus 3 times 1 plus 1. The left hand side x equals 8, that's 0. That's 0, you get C. So that gives you C equals 3 minus C equals 1. Okay? Now, to find B, for example, you differentiate this and substitute x equals 1. Because it's a polynomial true for every x. So differentiate each side. And substitute. It's the easiest one. Substitute x equals 1. So when you differentiate it, you get the left hand side 6x minus 3. On the right hand side, 2a times x minus 1 plus b, and the c is 0. Okay? So again, you can substitute x equals 1. Substitute x equals 1. You get 6 times 1 minus 3. This is 0. So that immediately gives you b. b equals 3. Okay? Now to find a, you differentiate it again. You differentiate it again and substitute. Let me move up here. Okay. So we differentiate it again. Differentiate again and substitute x equals 1. So if you differentiate again, the left hand side, x minus, you just need to differentiate it because other term is constant. Differentiate it, so the left hand side now 6, on the right hand side is simply 2a. That gives you a equals 3. You can also choose different values, but this is easier. Of course, you can use different values as well, yes. So in this way, we quickly find a, b, and c, right? So now you can write that rational function, 3x plus 1 over x minus 1 cube equals a is 3 over x minus 1, and b is also 3 over x minus 1 squared, and c is 1 over x minus 1 cube. Now integration will be pretty easy. Integral on the left hand side, 3x plus 1 over x minus 1 cube, integral 3 over x minus 1, 3 over x minus 1 squared, plus 1 over x minus 1 cube dx. Okay? Now we integrate term by term. There is 3 log x minus 1. And this one integral 3 over, so let me write it 3x minus 1 to the minus 2 dx, and x minus 1 to the minus 3 dx, and plus constant at the end. Okay, there's 3, to move up, 3 log x minus 1. So this one, 3x minus 1 to the minus 2 plus 1 minus 1 over minus 1. Here, x minus 1, the power rule, minus 2 over minus 2 plus constant. So that gives you the answer now, x minus 1, plus, here minus 3 over x minus 1, minus half x minus 1 squared plus c. Okay? So that, well, the integration, we have 3 terms, so you have to worry about that. All right, so now, a few minutes, I just want to do another example. So this idea will work actually in general as well. So this is, I'm just giving you a general formula. You don't have to memorize these things. We should know how to apply that, right? This is only one term here. All right, so in general, if you have the denominator, x minus a times k, if it repeated k times, you're going to have k terms, right? A over x minus a, a2 over x minus a squared, and a k over x minus a to the k. If the linear factor is repeated k times, you will be having k simple fractions on the right-hand side. Okay? So that's how it's done. Now let's look at another example quickly, the remaining time here. Have a look at this here. This one has powers of distinct linear factors. It case here. Now, so look at this x over x plus 1 cubed. You will see that here I have to use slightly different techniques to find a, b, and c. Okay, so 1 over x times x. So first check the degree of the polynomial at the top and bottom. That's fine. The degree of the bottom is higher. So that's the proper. That's been completely factorized. That's okay. You don't have to do anything. So how do you write the decomposition here? How many terms are we going to have here on the decomposition? Here. Exactly. Yeah. Excellent. Then 4, right? Because x is unrepeated linear factor. So you have a over x. Now this is repeated 3 times. You're going to have 3 terms. B over x plus 1 plus c over x plus 1 squared plus d over x plus 1 cube. You can think of x as x minus 0 as a linear factor, right? So they have 4 terms here. Okay, so now what we want to do, in the clearing of fractions gives you clearing of fractions both sides gives us. So what do you need to multiply both sides by x times x plus 1 cube. That gives you 1. A times you have x plus 1 cube, and b times x plus 1 squared. When you multiply here, c times x plus 1, here d times x. So this is true for now for all x. It's a polynomial equation. You can find the function a, b, and c any way you like. You can substitute some points in. You can compare the like term both sides the equation, or other methods as well. Okay, so what I'm going to do here, notice here, you have product of x terms in these last 3 terms. So if sub in x equals 0, these 3 terms will disappear, right? So you should be able to find a, right? So substitute x equals 0, right? So then the left-hand side is a. So a times 0 plus 1 cube. And this one is 0, this is 0, they all disappear. So that gives you a equals 1 straight away. So what is the other nice number which we can substitute to find the constant? Well, yes, exactly. Because x plus 1 term appears here in the 3 term, substitute x equals minus 1. X equals minus 1. So that gives you 1 equals, the first term will be 0, and the second term will be 0, and third term will be 0, and d times minus 1. So that gives you d equals minus 1 straight away. Now what do? We need to find another couple of nice numbers to get other 2 constants. So what we can do here, you can use 0 and minus 1. You can substitute x equals 1, for example, so that the number will be reasonable. Substitute x equals 1. So that gives you 1 equals a times 2 cubed, b times x equals 1, 1 times 2 squared, c times 1 times 2 plus d times 1. So that's going to give you an equation here. 1 equals ak plus 4b plus 2c plus d. We know already a and d substituted in. So that equals 1 equals h1, h plus 4b plus 2c, and d equals minus 1. So that's going to give you 4b plus 2c equals 2, that will be minus 6, right? 7 minus 6. Okay, we need one more equation to find b and c. So you need to choose another number, a nice number will give you a simple equation. What do you think would be the nice number? Which will give you a simple equation. Yes, you can do x equals 2. I think the calculation would be, yeah, you're right. You're right. Minus 2 would be easier. Substitute x equals minus 2. Substitute x equals minus 2. So if substitute x equals minus 2, 1 equals a times minus 2 plus 1 cube b times minus 1, minus 2, right? So minus 2, b times minus 2, x equals minus 2, minus 2 plus 1 squared, c times minus 2 plus 1, plus d times minus 2. Let's see what we get here. So that gives you 1 equals, that's minus 1, so it's minus a. Here, that's minus 1, 1, so minus 2b. And here, minus 2, minus 1 plus 2c, and minus 2d. We know that a equals 1, so that's minus 1, minus 2b plus 2c. d equals minus 1, so that is plus 2. So that gives you minus 2b plus 2c equals 0. So that means b equals c. Easy. So b equals c, use the first equation, so that's the second equation. So using 1 and 2, you can find b and c. Using 1 and 2, you will get b equals c, so 4b plus 2b equals minus 6, that gives you b equals minus 1. b equals minus 1 and c equals minus 1. So we got the coefficients, the constant there, now we can easily integrate that. So integral 1 over x times x plus 1 cube dx equals a equals 1 over x, b equals minus 1 over x plus 1, and c equals minus 1 over x plus 1 squared, and d equals minus 1 as well. So all three minus 1 over x plus 1 cube. That's the integral. That's pretty simple integral to deal with. So first one, 1 on x dx. This one minus 1 over x plus 1 dx. And this one minus 1 over x plus 1 squared dx. And minus 1 over x plus 1 cubed dx. We are doing it term by term. So that can be pretty easily done. Log of x, absolute value of x, minus log absolute value of x plus 1. And this one is minus 2 plus 1, plus 1 over x plus 1. So this one here, x plus 3 to the minus 2 over minus 2, plus constant. So that gives you the answer. Log absolute value of x, minus log x plus 1, plus 1 over x plus 1, plus half over x plus 3 squared, plus c. So that gives you the answer there. Okay, so that's how you find ABC. You see that sometimes, depending on the fraction, we may have to use different techniques to find the constant A, B, and C. So you have learned actually 3 different techniques to do that. There's one more thing we often do later on. I will show how that's done. Compare the coefficients of the like terms each side of the equation. All right, so just to finish up today's lesson, I'm going to ask you a question here and see how we can deal with that. So the idea, let me also say that the idea is the same. This is the general theory, but you don't really need to memorize these formulas or anything like that. So if you have a repeated linear factors, let's say x minus a1 is repeated k1 times, this one is repeated k2 times, and so on. Then in each one of them, you have a k1 terms for here. So for this one, you have k1 times simple fraction, and second one you have k2 times, and so on. So they are a similar number of fractions to do it. Okay, so just to finish up, here's the question for you. I'm going to leave that as my homework, but I'm going to ask this question. So you have to write down the form of the partial fraction. You are asked to solve it, partial fraction decomposition for the rational function. So it is important you should be able to know how to write down the partial fractions, right? Sometimes you may not be given the decomposition of the proper rational function. Have a look at this. I'll give you a couple of minutes to think about this. Look at this expression closely and answer this question. How many fractions are we going to have here when you write down the decomposition? How many simple fractions we are going to have here? Now you have to think carefully. Yeah, Abdullah is right. Yes, you're right. Okay, now, so first thing you want to do, check the degree of the polynomial at the top and bottom. Degree of the polynomial at the top is 4. Degree of the polynomial at the bottom, there is 3 plus 1, 4 plus 2, 5. That's higher than the degree of the polynomial on the bottom. That's fine, because that's a proper rational function. The second thing you want to do is to check the denominator has been completely factorized or not. Has it been completely factorized? That is fine. What about this? X squared plus 2x plus 1, which is x plus 1 squared, right? So you have to do the factorization first. 4x to the power 4 minus 3x squared plus x minus 9 over x cubed times x minus 7 and then x plus 1 squared. Now you can write the decomposition, right? So x is the decomposition now 4x to the power 4 minus 3x squared plus minus x to the 9, x cubed, x minus 7, x plus 1 squared. Now, your x cubed, it means x minus 0 cubed, right? That's the linear factor. Repeat it 3 times. X cubed, right? You already have 3 terms. So a over x, b over x squared, and c over x cubed. Okay. Now, x minus 7 is an unrepeated linear factor, right? So there's only one term, one fraction corresponding to that. So that is d over x minus 7. Now, this one, the linear factor repeated twice. So you're going to have 2 terms there for this. For this, you're going to have 2 terms. There's 1 here and 3 here. And e over x plus 1 and f over x plus 1 squared. So that's the decomposition there. If you look at the past exam questions, last year's paper, the first question is about asking you to write the decomposition. Okay? So you should be able to write down the partial fraction decomposition of that. All right. So that's it. That's enough for today. We will continue on Friday with other slightly difficult partial fraction there on Friday lectures. Now I will be around for another 10 minutes. If you have any questions on this lesson or previous lesson, I'm happy to answer the questions. Thank you. See you Friday. So we will continue this question on Friday. Yes, we will look at that for the partial fraction until Friday. Next week, we will start the new topic, ordinary differential equation. Professor Marcos will teach that topic Monday next week. This one, I will upload the solution. Let's answer you already here. We will have more examples to do Friday, actually. The other one slightly harder than this one.
Thanks, Jay. See you on Friday.
Okay, see you on Friday. Thank you.